Welcome back, everyone, to the start of part 3 out of 5 lectures on mathematical modeling of organic contaminants and subsurface remediation. So in the previous 2 parts, we looked at basic concepts of groundwater flow and transport modeling for a non-reactive contaminant. In this section, we'll consider a reactive contaminant. First, biodegradation in the context of multiple electron acceptors, as well as dissolving non-aqueous phase liquid. So from our previous lecture, you'll recognize our advection dispersion equation with a dispersive term and an advective term. And here again, we're solving for the concentration of our component alpha in the dissolved or aqueous phase. You recognize our decay term here as before. In this case, we'll expand on this lambda term, which will now become nonlinear in the context of multiple components and multiple electron acceptors. We've also added this dissolving source term, which is a source with respect to our aqueous phase liquid, our aqueous phase dissolved phase contaminant. So we have a dissolving NAPL residual phase here, say trapped between some grains, and we want to add this source term to our aqueous phase concentration. So a simple formulation for that is just a rate term here times a concentration gradient or change in concentration here. So this change in concentration is just the difference between the solubility concentration at the surface of the NAPL phase, which is given by Raoult's law, function of the pure phase solubility and its mole fraction. So we can calculate this at every time step. So the difference between that concentration and this aqueous phase concentration, which is part of our solution. The coefficient here, the rate term, many formulations for this, and here we've got a function of NAPL saturation, a grain size diameter term, a diffusion term in the NAPL phase, and a Sherwood number, which controls the rate. So by adjusting the Sherwood number and having a function of different terms here, we can change the rate of dissolution. And a common assumption is that this rate is very high, which will give us a dissolved phase concentration in the pore water here next to the NAPL at its solubility limit. Let's look a little more carefully at this decay term now in the context of multiple components. So here's the conceptual model, or one conceptual model that we can use in the context of many substrates. In this case, let's say we have 3 gasoline components, benzene, toluene, and xylenes, again in the aqueous phase. And together in the pore space, we have several electron acceptors. Let's say we have 2, oxygen and nitrate. And associated with each of these electron acceptors is a microbial population. So we have our advection dispersion equation, which we can use to solve for these substrates. And at the same time, this advection dispersion equation can be used with some small modifications to simulate the electron acceptors, because they're also dissolved. So this lambda term here, which we introduced the Monod formulation in the previous lecture. So this is what we'll use in this case for our organic substrates, in this case for C alpha. So our lambda for our biodegradation term will be a function in general of each electron acceptor. So we have a sum over each electron acceptor because each component can actually be degraded possibly by several electron acceptors. So we need this lambda term now to be a function of the electron acceptor of each electron acceptor, A, as well as some other terms here involving the concentration of its component. So for our lambda, we have a rate term. It has to be dependent on the microbes as well. If there are no microbes, we can't have any degradation. Our half utilization rate term here is a concentration we can use to adjust this function. As I mentioned before, the Monod term gives us a way of changing the reaction order as a function of concentration. So at low concentrations, the Monod term gives us a first order. At high concentrations, it gives us a 0 order, where it's already reached its maximum rate term, biodegradation rate, because it's now no longer dependent on the concentration. We can have inhibition terms as well, where one component can inhibit the degradation of another inhibition term here. But in general, now this term becomes nonlinear because it's affected by each of the other electron acceptors. And it's also being transported, this component, with the other components that are there, the other substrates, and which are also consuming electron acceptors. So this becomes a multi-component, multi-electron acceptor nonlinear problem. As I mentioned, the electron acceptors are also in the dissolve phase, We can also use the same advection dispersion equation to solve for that with just a change in the degradation term here. Basically, we add a stoichiometric coefficient, which tells us that for each mole of substrate degraded, we'll have X moles of electron acceptor consumed. And this stoichiometric coefficient here is obtained from our reactions. If we assume they go to completion, for instance, here we have benzene and oxygen. So 15 divided by 2, or 7.5 moles of oxygen are used for each mole of benzene consumed. And here, say 6 moles of nitrate are used per mole of benzene. So we include these stoichiometric coefficients as a mass ratio in our model. This is an example of a coupled nonlinear model because we have multiple components. We also have a possible effect of a dissolving NAPL, of the dissolving NAPL saturation on the hydraulic conductivity. We have a source term. We have a dissolving NAPL. As the NAPL dissolves, it will free up pore space, which will change the hydraulic conductivity of the porous medium, which changes the flow system. So we have to couple our transport model with the flow model. We've seen already these reaction rates in this case are nonlinear, so they have to be coupled within the transport code. Also, these reactions are going to change generally the pH. They can change the CO2, which will have an effect on the aqueous inorganic geochemistry. So possibly we need to include the inorganic chemistry as well. And there's several models that can do this, some of which are mentioned here. Just to show an example here, we've got a vertical 2D section with a source term at the water table. And there's several methods or approaches to include a source term. One of the simplest is to assume a mixing cell for our source zone. This is a dissolving residual NAPL phase, say a light non-aqueous phase liquid resting on the water table. And we have a flux passing through this source zone. And we can assume a solubility concentration coming off the bottom of this based on Raoult's law. And with a simple mass balance across this, we can, at every time step, delta T, calculate the mass remaining in the source zone. And we can use this concentration coming off the source zone as our third type boundary concentration going into our porous medium. So in this context of a flow system at steady state, here's an example of toluene evolution in the context of degrading with 3 electron acceptors, nitrate, sulfate, oxygen, nitrate, and sulfate. So here we have a toluene plume coming off our dissolving NAPL source zone. Here the concentrations here in parts per million. This is vertically exaggerated by a factor of 10, by the way. So with this toluene, it's consuming oxygen. So here's an oxygen depletion plume. So we have pretty well 0 concentration here. This plume is only plotted for where the oxygen has been depleted. So this oxygen background here is a background level of about 2 milligrams per liter. And then everywhere inside this shadow plume, it's being depleted. And this is governed by our advection dispersion equation as well. You have dispersion. Now it's dispersion towards the interior of this consumed plume because the concentrations are higher on the outside. And you have advection and dispersion longitudinally as well. And here's the reaction that governs that equation, the reaction that governs the behavior of toluene and in the presence of oxygen. Now in this conceptual model, we've got also nitrate as a potential electron acceptor, so it's being consumed as well, but in this case only in the zone where oxygen is being depleted. So we have a nitrate depletion plume. Again, nitrate is present in this background, up to concentrations of, say, 8, in this case 8 milligrams per liter. And finally, we have sulfate, a sulfate depletion plume, where nitrate has been depleted. Here, background nitrate is 20 milligrams per liter, and it's being consumed down to 15 in this case. So this is an example of a single component with 3 electron acceptors. In this conceptual model, we've also added methane production from CO2. So here's a positive methane plume. And as I mentioned in our conceptual model, we have a microbial population associated with each of the electron acceptors. So here I'm just showing the microbial growth pattern. And this is a typical pattern that comes out of modeling. We have microbial growth on the fringe of the organic plume, and within the fringe of this oxygen depletion plume. So microbes can only grow where there's enough toluene, enough substrate, in this case toluene, and enough oxygen. And the only place that can happen in this conceptual model is in the mixing zone. So here there's enough toluene and there's enough oxygen at the same time. Inside, the growth is less because there's enough toluene, but there's not enough oxygen. And outside, there's lots of oxygen, but there's no substrate. So we can use these kind of conceptual models to test different behaviors, test the model, test for mass balance, and so on. Again, we're looking for these high concentration gradients controlled by low vertical dispersivities, and we hope to check for mass balance as well. There's another conceptual simulation showing these 3 anaerobic zones. Here the oxygen depletion zone, nitrate reducing zone, and a sulfate reducing zone. And these will evolve as the plume grows, and possibly if the plume disconnects, if the source zone becomes depleted or completely dissolved, then we'll see different behaviors, and we'll see this in a few minutes. So here's an example, conceptual simulation of a gasoline plume with some ethanol added to it. These are all at 600 days. This is a single simulation. So we have to transport, in this case, benzene, toluene, and a bulk component, which represents all the remaining components of gasoline. This is dissolving from an interior residual source zone here, defined by this box. Now, being a mass balance model, and since the dissolving contaminant here, the concentrations will depend on the mole fractions of each component, we need to include the entire mass of our source, which is why we need to include this bulk component. So all the other components here make up the rest of our initial mass. But in this case, let's say we're only interested in benzene and toluene, say the two of the more mobile and toxic contaminants of our source here. In this case, we've added some ethanol, and all these components are transporting with a single electron acceptor, oxygen in this case, and a single microbial population. So we see immediately different behaviors here from the model. We see, first of all, that these components are dissolving at different rates because there are different transport distances from the source zone. And this one is disconnected, for example. Actually, ethanol is being the most soluble. It's completely miscible in water. It's detached completely from the source zone after 600 days, or well before that, in fact. It's dispersed quite a bit, and it's transported quite far down gradient, being not retarded. Benzene is the next. It's still dissolving from the source zone, or almost. Perhaps it's completely dissolved, but it's extended back because of dispersion. Hasn't traveled quite as far as the ethanol plume because there's a retardation factor. Same thing with toluene. It's even still dissolving from the source zone. It's less soluble, and perhaps there was more toluene in the initial mass of the source. It's also retarded, perhaps a little more. And the bulk is retarded even further, and it's still dissolving from the source zone even after 600 days. So we can look at this at a simulation like this and already get some handle on system behavior. Here's the oxygen depletion plume after 600 days. It tends to follow this ethanol. In this case, ethanol is consuming a lot of the oxygen. And in fact, this was the objective here, to look at the effect of ethanol on consumption of oxygen and degradation rates of the other components. So this oxygen depletion plume will also migrate down gradient. It's not retarded, but it's undergoing dispersion as well. And we have the microbial growth, again, highest near the source zone, where we have this continuous long or slow dissolving source zone, as well as a complete continual replenishment of oxygen from up gradient. So we have a good replenishment of oxygen here, a long-term source of organics, so we have some strong microbial growth, and then growth along the fringes again. Again, good dispersion characteristics here, giving us a good simulation. The previous case was for a homogeneous system. You can also look at heterogeneity. It's a common approach to build in these low K or high K zones in our system. Here's a conductivity plot, log K. So in red here we have some high K zones, maybe some coarser sand And in blue here we have some less permeable material like a silt or a clay. So we can look at plume evolution in this context. We have a toluene source, oxygen being depleted, and microbial growth. This is after 10 years in a heterogeneous system. So we see some variation here now of our concentration gradients, which tends to enhance mixing and enhance biodegradation. I have a few animations to show, two animations, one for toluene, one for oxygen I can show. Here's the animation for toluene as it evolves, as it's dissolving from our residual source zone, and it's biodegrading with oxygen. So over time, it completely dissolves from the source, and it actually starts to reverse direction here because of consumption by biodegradation. That's the toluene. Here's the same simulation showing the consumption of oxygen. So again, from our residual source zone, toluene is dissolving and consuming oxygen here. Background oxygen is always being replenished, so we have dispersion towards the zone of oxygen depletion. So that's the end of part 3, and please come back for part 4. Thank you.